Hello. Do you remember in the previous video how a certain form of the Nernst equation tells us how the concentration of your various aqueous ions will affect the voltage of a cell, an electrochemical cell? Good, because in this video we will talk about some applications of that, of the concentration dependence of the voltage. So one application is concentration cells. And so these are a galvanic cell, like just the things we've been talking about, those things, from two half cells that are identical, except that the ion concentrations are different. So for example, you can take a cell diagram like this. Remember the oxidations on the left, the reductions on the right. And so this tells us that what's oxidized is the zinc solid going to zinc ions, and what's reduced is the zinc ions going to zinc solid. And so you can put this together. So the overall reaction is in one half cell, you'll have the 1 molar zinc solution. In the other half cell, you have the 0.1 molar zinc solution. And assuming this is spontaneous, which it probably is, the way it's written, it means that this concentration is going to go down, this concentration is going to go up, and presumably the reaction will hit equilibrium when the concentrations are the same. And so another way to think of this is that the half cell with the higher concentration is reduced because the greater concentration of zinc will push this reaction to the right, just like Le Chatelier's principle tells us. All right, so ultimately, two half cells that are the same, different concentrations, wire them up, you get a voltage out of it. So let's think about how to calculate that voltage. And so we're going to use this form of the Nernst equation. And our Q here, right, so this term is Q. Our Q is going to be product ions, so it's the dilute one, divided by reactant ions, so it's the concentrated one. And neither of these are squared, so there's no coefficients up here. All right, and then E naught here is going to be 0, because whatever standard cell potential there is for this half reaction, it'll just be the opposite in sign for this half reaction, and they will add to equal 0. And that's okay, because it's a concentration cell, you would expect these things. And this is a bunch of constants. N is equal to 2 for this reaction, because there's 2 electrons right here. And I put the concentrations in. And so this is equal to 0.03, say, volts. So that's a small amount of voltage, but it does show a point, is that you can legitimately make a cell from two identical half cells, except the concentrations are different, and you'll get a voltage out of it. So that's an interesting application. All right, the other application we'll talk about in this video is how to get ion concentration from cell voltage measurements. And so this involves the Nernst equation, which is what we're talking about, in either form, depends on what you're given and what you feel like using. Now, looking at this, if you know what the chemical reaction is and you have a list of standard reduction potentials, then you can determine what E naught is from the standard reduction potentials. You know the constants, and you know the number of electrons transferred. And so you know all of this. And so if you measure a voltage over here, then you can solve for Q. And then once you know what Q is, you can then deal with the two ions here. So if you know the concentration of one, you can find the concentration of the other, and vice versa. So basically, this is just using the Nernst equation and solving for Q and something inside Q. So some textbooks don't even make a section about it. Your textbook does, which I appreciate, actually, because it's nice to have it presented to you differently. But ultimately, let's just give this a try. It's something that I could have asked you to do without this video, but we might as well put it in the video. Okay, so say we have this reaction, zinc solid and silver +1, silver plus, in a reaction, and then you measure some cell voltage of 1.37 volts, and you have a concentration of the zinc ion, and now you want to find what the silver ion concentration is. And you'll need the standard reduction potentials to pull this off. All right, so we're using the Nernst equation here, and we're going to solve for this first. We'll calculate this number first, and then we'll put all the constants in. We measured 1.37 volts. We'll solve for Q, and then we'll go from there. So looking at this, the zinc is oxidized because its charge goes up. The silver is reduced because its charge goes down. And so these are reduction potentials, or reduction voltages, same thing. And so we're going to switch this reduction of zinc to an oxidation. In doing so, this negative becomes a positive. All right, then we have the reduction one that we don't change because it's getting reduced, so it doesn't need to change. Number of electrons is equal to 2 in this reaction. We'll need that later. And then you add these two half reaction voltages together, and you get the standard state cell voltage for this combination of half cells, 1.56 volts. Now this is standard state at 1 molar. We're at not 1 molar, and so that's why we definitely need to use this form of the Nernst equation. All right, so now let's carry on. You can tell this came from an answer key. And so we have the Nernst equation, and then I wrote out what the form of Q is, right? Q is just like an equilibrium constant, except not equilibrium concentrations. And so you put products, so products, the zinc, right here, divided by reactants. Notice that the silver has a 2, and so we need to square the silver. Don't forget that. It's easy to miss those. But we don't need to square the zinc since there's no 2 right there. Now we go and plug everything in. We measured 1.37 volts. This we just calculated, E naught. Here's all the constants. Number of electrons is equal to 2. And then natural log, and then what's on top? Zinc is on top. We know the concentration of the zinc 2+ ion. And we're just trying to solve for whatever this is. So now it's just a fancy game of solve for x. And so to do that, well, we'll subtract 1.56 from both sides, which leaves us with negative 0.19 on the left. Plug all these numbers together and get the ultimate output, which has units of volts. And then plug the zinc concentration that we know into here. Then if you divide by 0.012, you get this number. And then if you take E to both sides, you get this number for the left, and then it makes the natural log go away on the right. So then now you kind of multiply both sides by the silver, divide both sides by that, and then you get this value of silver concentration squared. And then you take the square root of that, and then you have 6.1 times 10 to the negative 5th molar. So that tells you something. That tells you what the silver ion concentration is at this given moment in time, because E cell will change as the reaction proceeds, which makes sense because our concentrations change as the reaction proceeds, because otherwise it wouldn't really be a reaction. So basically this part is just, actually both the things in this video are just an application of the Nernst equation, specifically this form of it. And so keep that in mind, add that to your toolbox of things that you know how to do, and you'll be fine. Thanks for watching.